So now we're going to look at some applications of these exponential functions, mostly with populations. So we're going to look at populations of bacteria, animals, humans, whatever it is. We're going to have two types of growth. You can have uninhibited growth, which means there's nothing stopping it. And then you can also have limited growth, which means there's kind of a cap-off point for where it can go to. So we're going to consider this exponential function, f of x equals e to the, or 2e to the 3x. So we're going to look at its derivative. So the derivative, f prime of x, would be, well, the exponential function, you get exactly itself back, and then chain rule tells you you've got to multiply by the derivative of the exponent. Well, really, this 2e to the 3x is exactly the function you started with. So the exponential function is really nice in that it's always going to satisfy what's called this differential equation. So function y equals f of x satisfies that the derivative is a constant times the original function. So the way you can think of this is f prime is a constant times the original function f. The only type of function that will satisfy this equation is the exponential function. So it's a constant times the exponential function, okay? So anytime you have this form where y prime is a constant times y, dy dx, all those represent exactly the same thing, the solution is going to be your exponential function. And the value that you have right out front, this k value, is what becomes the exponent in the exponential function, because that's what pops out from chain rule. So let's look at an example. We're going to find a function that satisfies the equation, the derivative of a with respect to t, so that's going to be our variable, is 5a. So this is the same saying dA dt is a prime of t. It's 5 times a, which is a at t. So the function that satisfies this equation is some arbitrary constant, and this 5 becomes the exponent. So you get 5 to the t. So you can always check this by just taking the derivative. You get exactly the function back, the constant stays attached, and then chain rule, you have to multiply by the derivative of the inside, okay? So types of functions that satisfy these equations would lead to some type of uninhibited population growth. So basically, this model tells you that the population is going to grow exponentially. You can kind of think of it really as what's going on right now. Every single day there's more and more cases of COVID-19. It's got an exponential growth associated to it, and it doesn't have a cap off. That's what we want it to happen, but it's not. So it's just continuing on going and going and going and going. So basically, the population each year is going to increase proportionally to the previous year. So anytime we have this equation to represent our population, dp dt is some constant times p. The solution to it is going to be the exponential function. And k is going to be the rate that the population is growing, so our growth rate. But it's going to be expressed as a decimal. So if you go ahead and look at the solution to this equation, if you plug in 0, you get p of 0 is equal to c e to the 0, and e to the 0 is 1, so you get c. So we call that our initial population, which we're going to denote by p sub 0, so 0 representing initial. So our general solution for this uninhibited population growth is given by p of t equals the initial population times e to the growth rate times the t. So you can apply this model to human populations, bacteria populations, business models. You can apply it to infectious diseases as well. There's a lot of neat applications to it. Okay, so let's look at some examples. Suppose P0 is the amount you're going to invest in initial savings account. and it's going to have interest compounded continuously at 6.8% per year. So basically the balance grows at this rate. So the rate is the derivative, dB dt. You get an additional 6.8% each year. So its rate is 6.8% of the previous year. So what we want to do is we want to find a function that satisfies this differential equation. And we want to write it in terms of the initial amount we invest, P0, and this rate. Okay? So we have the exponential function, the constant out front of P becomes your exponent. So the function that satisfies it is P of T equals the initial amount times E to the growth rate, which is 0.068 times T. And you can go ahead and check it, take the derivative, you get exactly the same function back, but chain rule tells you you have to take the derivative of the inside, and the derivative of 0.068T is just the constant. So you get the differential equation back, right? So let's apply this now. Suppose maybe we invest $1,500. Let's see what's in our account after 1 year. So this $1,500 is just going to be the initial amount. So P of T, the P0 is going to get replaced by 1,500. Okay. And then if we want the balance after 1 year, we're going to replace that by 1. So you get 1,500 times e to the 0.068 times 1. And if you plug that into your calculator, you get about $1,605.55. So basically, after 1 year, you'll have gained $105.55 in interest. Okay, so this is the total balance you have in your account. So we want to see now, if we do have a $1,500 investment, when is it going to double? So basically, we're looking for the time when the amount in our account is $3,000, okay? So basically, we've got 3,000 as our output, 1,500 is our initial input, and then we've got e to the 0.068t. We want to solve for t, so we're going to divide both sides by 500. And what that's going to allow us to do is cancel these out, and you just get 2 is equal to 0.68t. You want to take the natural log of both sides to get rid of the e. So natural log of 2 is 0.068t. So to solve for t, you divide both sides by the 0.68. So you get t is the natural log of 2 divided by that growth rate. So it'll take about 10.19 years for you to double the amount of money in your account. So this is a very specific example, which you might have seen back in college algebra. It's when you have continuously compounded interest. So your general formula is going to be P of T is equal to your initial amount times e to the RT. All of the different pieces stand for something. So P0 is your initial investment, R is your interest rate. You want to make sure you enter that as a decimal. T is the time, and that's going to be in years. And then in general, if you want to find that doubling time, here you saw it didn't really matter what you invested. If this was if this was 1,000 you would have invested, you would have put 2,000 over here. If this was 3,000 you invested, you would have put 6,000 on the other side. And regardless, you're always going to end up with this equation, 2 equals your rate, e to your rate times t. So you can kind of generalize this to know that if you want to find the doubling time for any exponential growth, doesn't have to necessarily be just with your accounts. It can be with populations as well. What you're going to have is t is equal to the natural log of 2 divided by the growth rate. And likewise, if you want tripling time, you'd get natural log of 3. Quadrupling time would be natural log of 4. So it's just the natural log of whatever rate you're dealing with divided by the growth rate. Okay. So do a quick example. A bank advertises that it compounds interest continuously and it will double your money in 15 years. You want to figure out what is the annual interest rate that it's going to be charging or giving you. So all that is the time is 15 years. It's doubling, so it's going to be natural log of 2, and k is our unknown. That's our growth rate or interest rate. So rearranging the equation, the growth rate's natural log of 2 divided by 15. And if you plug that in, it's about 0.046. So you're getting a 4.6% rate on that account. Okay. Now, realistically, most of these uninhibited growth are pretty bad. Most places or most populations have some type of limit, whether it's some type of food resource, could be just land, it could be there's prey involved. There's going to be a limit as to what that population can reach. So that's going to be something that's called a carrying capacity. So basically you're going to have a limiting value L that your population's not going to be able to exceed. So if we kind of look at a graph for this, you've got your initial population starting at P0, and this value of L up here is the limit. So your population can exceed that. If it does, it'll end up dying out because you don't have enough resources to sustain that population. So the idea is you're going to start by having some exponential growth, and then if you get too close to this limiting value, it's going to have to cap out and it's going to smooth. So it's got some exponential component to it, but then eventually it has to plateau. So these are called logistic equations. They're going to have this form, and they're not as set in stone as the uninhibited growth is. They might have some constant in place of this one. Could be a bunch of different things, but you're going to have that exponential function in the bottom. So these ones you're not going to ever come up with the equation. You're going to be given the model that works for that particular group. So let's look at an example. We've got a tortoise population in a square mile of the Mojave Desert. So this population is P of T. You can measure how many tortoises are in this location after T years by this logistic equation. Right? So we want to start just by figuring out what is the population after 0 years, after 15 years, and so on. So first, if you want the population after 0 years, so that's your initial population, you just plug in 0. And the only place that involves t is right down here in the denominator. So simplifying this, you get 3,000 over 20 plus 130. It's 3,000 over 150. So initially in this 1 square mile, you have about 20 tortoises in the desert. After 15 years, all you would do is replace the t by 15. And I'm going to trust if you plug this into your calculator, you're going to see it's about 119 tortoises. So what we want to do now is we want to see what is the rate of change of the population of these tortoises. Okay. So we've got our initial function P of T. If you rewrite it a tiny bit, this is in the denominator. So you just get the denominator to the -1 power. So if we want to differentiate this, you've got a function in a function. So it's this function inside that power. You've just got to apply power rule. So the -1 comes out front. You keep all of this exactly the same, but the exponent just becomes -2. But then chain rule tells you you've got to take the derivative of the inside as well. So if you do a little bit of cleaning up, now you can bring this -2 power in the denominator as +2. The derivative of the inside, you get 130e to the -0.214t, so the derivative of 20 is 0. But chain rule again tells you you have to multiply by the derivative of the inside. So you get that extra -0.214. So just a little bit of cleaning up. If you multiply the 130 and the 0.214, you get this negative 27.82. And then if you multiply the 27.82 with the 3,000, you get this function here. So this tells you the rate of change of the tortoises. Now what we want to do is we want to find the rate of change in the population. Now what we want to do is we want to find the rate of change in the population after 0 years. So all we want to do is plug in 0 for t. So this t becomes 0, this t becomes 0. So you can clean this up a little bit. E to the 0 is just 1. So you get 83,460 in the top. The bottom becomes 20 plus 130. So that's 150 squared. And then if you plug that into your calculator, this is a rate. So after 0 years, your rate of change is about 3.71 tortoises per year. So your population's increasing by that amount. If you looked at a different year, say after 15 years, it's probably going to be a little bit less because it's going to have to reach that plateau. So it's got that shape where, oh, I'm increasing a lot, and then for later years, I've got a plateau out. Okay? So the last thing we want to do is we want to find the limiting value for the population of tortoises. So what that means is we want to see, as the time goes on forever, what does the population tend to? So what is it going to kind of cap out at? So to do this, you want to remember what that graph of e to the x looks like. So we're going to let t go to infinity. We're going to need to know what's happening potentially. So we need to take the limit as t goes to infinity of a population function. So all that is the limit as t goes to infinity, and then our population function is 3,000 over 20 plus 130 e to the negative 0.012. So this component down here is the only thing that involves t. We need to see what's happening to that. So I don't like that exponent where it currently is. I'm going to rewrite it. So you have e to a negative power. You bring it down in the denominator. And now maybe you can kind of see from the graph, use a different color, t is getting larger and larger. So this is going to be e to a very, very large number. So it's going to blow up to infinity. So what happens in the limit is the 130 over the exponential function just tends to 0. So this whole thing goes to 0 in the limit. So you get 3,000 over 20 plus 0, which simplifies to just 150. So what that means is the population of tortoises has a carrying capacity of 150. So when it reaches that amount, it's going to kind of plateau. If you try the rate of change at any other value close to there, you're going to see that it's very, very small. So basically the tortoise population isn't going to be changing. Okay? So these are two main types of models that we're going to deal with. In the next section, we're going to see kind of the reverse of this. So this is constant increase or exponential increase. We're going to see about decay.